Okay, in this problem, what we're going to do is we're going to solve a two-dimensional collision problem using the momentum method. So in this particular problem, what's happening is these two masses are on a frictionless surface. The 1 kilogram mass is moving 5 meters per second at an angle of 53 degrees relative to this vertical here, and it collides into this 2 kilogram object that's not moving at all. Afterwards, the 2 kilogram object moves directly to the right, and the 1 kilogram object moves directly downward. We're asked to find what the velocities are of each of the masses after the collision. So we will follow the momentum method in 2 dimensions. So let's start off with the horizontal direction. So the first thing we're supposed to do is draw a labeled picture with components. So the 1 kilogram mass is the only object that's moving, and in the horizontal, it's got a velocity of 4 meters per second. So what we have to do is we have to use a sine function to figure out this component of the velocity, because that's the horizontal component of this 5 meter per second velocity that's going at 53 degrees. So 5 meters per second times the sine of 53 degrees, because it's opposite that angle. That's why we're using sine, gives us 4 meters per second. So that's our picture. That's step number 1. Step number 2 is determine what direction is positive. We'll say to the right is positive. Then step number 3 is to look at the bar graphs. So in our bar graph, again, we're just looking at the horizontal. The 1 kilogram mass is going 4 meters per second. So the momentum in the horizontal for the 1 kilogram mass is its mass, 1 kilogram, times 4 meters per second. So that gives us a momentum for the 1 kilogram mass of 4 kilogram meters per second. 1 times 4 is 4. The 2 kilogram mass before the collision is not moving at all, so it has no horizontal momentum, nor does it have vertical momentum for that matter. Afterwards, the 1 kilogram mass is moving straight down, so it's got no horizontal momentum afterwards. The 2 kilogram mass is moving to the right, so we're trying to figure out what this momentum is for the 2 kilogram object after the collision. Well, we know that because the system is frictionless and because there are no external forces, and the reason there are no external forces is because the system is frictionless. It's a closed system. Since it's a closed system, the momentum must be conserved. So all the momentum before the collision for both masses was 4 kilogram meters per second. So after the collision, the momentum for both masses must be 4 kilogram meters per second. Because the 2 kilogram mass is the only object that's moving, it's the only one that has any momentum. So the 2 kilogram mass has a momentum of 4 kilogram meters per second to the right. Step 5 doesn't apply because it doesn't specifically tell us it's elastic, because the kinetic energy, it doesn't tell us that the kinetic energy is the same before or after. It doesn't tell us that it sticks together, so therefore it's not inelastic. However, momentum is still conserved. So step 6 is to write our equation that says the initial momentum horizontally has to be equal to the final momentum horizontally. Then number 7 is to write out our equation. So that's M1, the 1 kilogram mass, M2, the 2 kilogram mass. Those are the each momentum or each momenta before the collision, and here are the momenta after the collision. Now again, we know that the 1 kilogram mass is going 4 meters per second before the collision. The 2 kilogram mass is not moving at all. Afterwards, the 1 kilogram mass is not moving horizontally, at least, and the 2 kilogram mass is moving horizontally. We're looking for this horizontal component of the 2 kilogram mass's velocity. So since the left-hand side is 4 kilogram meters per second, I set that equal to 2 kilograms times the horizontal velocity of object 2. If I divide both sides by 2, I find that I get a velocity of 2 meters per second for the 2 kilogram mass horizontally. So now we're done with the horizontal part of that Now let's look at the momentum in the vertical direction. So again, before the collision, only the 1 kilogram mass is moving. It's moving at 5 meters per second at 53 degrees. But we only want its vertical component. So its vertical component would be the cosine side of this triangle right here, or the adjacent side. So we're going to use the cosine function and go take 5 meters per second and multiply it times the cosine of 53 degrees to get negative 3 meters per second, because it's going downward. The 2 kilogram mass isn't moving at all, so it's got no vertical momentum. So only the 1 kilogram mass has any momentum, and its momentum is 1 kilogram times negative 3 meters per second, so that gives us negative 3 kilogram meters per second. 2 kilogram mass, again, has no momentum before the collision. After the collision, the 2 kilogram mass is only moving horizontally, so it does not have any horizontal momentum. So therefore, it has no vertical momentum. So all the vertical momentum must remain in the 1 kilogram mass. So if we look at so let's change this. Let's say that instead of downward is positive, let's say upward is positive. So if we look at the picture, therefore, that's why these values are negative. Okay, so I'm going to change this so that it says downward is negative or upward is positive. So our equation for part 6 is still that the total momentum before the collision equals the total momentum after the collision. This is our filled in equation here. We've got 1 kilogram times negative 3 meters per second plus the 2 kilogram mass that's going 0 meters per second. Again, it's not moving before the collision. After the collision, the 2 kilogram mass is not moving vertically. It's only moving horizontally, so it's got no vertical velocities. That's why there's a 0 there. So we get negative 3 kilogram meters per second is equal to 1 kilogram times the vertical component of the velocity. So we just get v is equal to negative 3 meters per second. So we figured out that the 2 kilogram mass is moving horizontally at 2 meters per second. The 1 kilogram mass is moving vertically downward at negative 3 meters per second. This last part asks us, in a clear, coherent, paragraph-long explanation, justify the fact that the momentum is conserved in the horizontal direction. So what we would say is we would always start off with our answer, and our answer is that the net horizontal momentum before the collision is equal to the net horizontal momentum after the collision. Since the masses are on a frictionless surface, the system is closed. As we know, in any closed system in which there are no outside forces acting on the system, the linear momentum must be the same before and after any collision.